Welcome back to the wonderful world of astronomy. We are in Chapter 4, Making Sense of the Universe, Understanding Motion, Energy, and Gravity. And Chapter 4 is laying down the fundamental concepts necessary for understanding astronomy. This video is Part 3, Energy. Energy is something that's very difficult to define. It's more useful to look at examples of energy as we learn about it. But a description of energy that will be useful for us in this class is to think of that energy makes matter move, or at least it's something that can make matter move. An important concept when we deal with energy, when studying physics, is that it is conserved. And we've come up with conservation laws before. You've seen conservation of momentum and conservation of angular momentum. Well, there's also conservation of energy, and it's probably the most often used principle in all of physics. So it's conserved, it can be transferred from one object to another, and it can also change form. And we will look at various forms of energy. There are three basic types of energy or categories of energy, and the first one is kinetic energy. Now, when you see the word kinetic, it has something to do with motion. There's kinesiology, which is the study of the body's motion. But kinetic energy is energy of motion. When something is moving, the fact that it is moving means that it has energy associated with that motion. So you can imagine a rock that's falling from a great height or from a small height. If it's falling, it has motion. A car speeding down the road, a planet orbiting the sun, if it's moving, it has kinetic energy. The second category or type of energy is potential energy. Potential energy, think of it as stored energy. The potential energy it has, what it usually looks like is it's not actually doing anything at the moment, but it's stored based on the shape, the configuration, maybe the position of the object. It's got energy stored in it. So a minute ago, I gave an example of kinetic energy, a falling rock. Well, where did it get that energy from? If the rock was on the top of a high cliff, just sitting up there, wasn't actually doing anything, just sitting there. But by virtue of its position high above the ground, it had potential energy. So the idea of conservation of energy is that rock can fall. And falling down, it loses potential energy and it gains speed, it gains kinetic energy. I gave an example of kinetic energy of a speeding car, but where does the car get that kinetic energy? Well, from gasoline. You imagine a can of gasoline, it's just sitting there, not doing anything, but locked inside of the molecules, the molecular bonds within the gasoline, is energy that's stored. So there it's based on the configuration of the molecules. Another example of potential energy is a spring or a rubber band. If you want to shoot a rubber band across the room, you put it around your finger and you pull on it. And in pulling it, in stretching a rubber band, you are giving it potential energy. And if you let go of it, that potential energy will become kinetic energy as it flies through the air. A spring, you compress a spring so that it has the potential to spring back. Or you stretch a spring, just like stretching a rubber band. It has potential to spring back. So based on its shape or configuration, you're giving it potential energy. The third type of energy is called radiative energy, or simply radiation. And you can think of it as light. Although it's more than just visible light, it can be visible light, but it also includes X-rays, radio waves, ultraviolet, and other types of radiation. In Chapter 4, we will look more at kinetic and potential energy. We're going to save radiative light for Chapter 5. I want to now look at three specific examples of energy that are useful in understanding astronomy. And every specific type is going to fall into one of the three categories that I just mentioned, either kinetic, potential, or radiative. Let's look at the first type, thermal energy. And this falls into the broader category of kinetic energy. Thermal energy is the collective kinetic energy of many particles. For example, in a rock, in air, or in water. You look at the picture down below, and this is some object, some piece of matter, doesn't really what type of matter it is, it doesn't matter, but it's got molecules in it. It's made up of many, many, many molecules, and they're all moving around at some speed. So every one of those little molecules has kinetic energy. The thermal energy, as we now zoom out to the whole object, the thermal energy is the kinetic energy of all the little molecules, all the little particles. It is related to the temperature, but it isn't exactly temperature. We can say the temperature is a measure of thermal energy. Temperature is actually the average kinetic energy of the many particles in a substance. Now, kinetic energy of any particle or any object is based on its mass and its velocity. So these particles, as you look in the picture, it looks by the picture, I think the author intended them all to have the same mass. So let's focus on velocity. On the left, they're moving more slowly, and that's shown by the shorter red arrow. They don't have as much velocity as on the right. And so the molecules on the right have a greater kinetic energy on average, and that's going to be a higher temperature object. We should be familiar with temperature scales. Certainly living in the United States, you're familiar with Fahrenheit. And so water freezes at 32 degrees Fahrenheit and water boils at 212 degrees Fahrenheit. And that actually is what defines the Fahrenheit scale. It's 180 degrees between water freezing and water boiling. You can get colder and colder and colder, and you can get down to what's called absolute zero. Now, on the Fahrenheit scale, that's negative 459.67 degrees Fahrenheit. Absolute zero is the coldest possible temperature that can occur in the universe. Now, that sounds very weird to think that there is a coldest possible temperature, that something can be this absolute zero temperature and that it cannot get any colder. That sounds weird, but if you think about what temperature is a measure of, temperature, remember, is a measure of average kinetic energy of particles. It's a measure of motion of the particles. And so when you have a situation where something is 0 Kelvin, that just means that all the particles are slowed down so much that they've gotten down to 0 motion. And when they have 0 motion, that means 0 Kelvin. And you can't get any colder than that because you can't get any slower than having everything, all the motion stopped. So that is the coldest. Now moving to the middle of this picture, there's the Celsius scale. Celsius is defined as water boils at 100 degrees and it freezes at 0 degrees. And on this scale, absolute zero is negative 273.15 degrees Celsius. What is used most often in science, and you'll be hearing much of it in this class, is the Kelvin scale. Now, the Kelvin scale is based on the Celsius scale. It's just been offset by 273.15 degrees. What I mean by that is this. 100 degrees Celsius, add 273.15, and you've got Kelvin. 0 degrees Celsius, add 273.15, and that's the Kelvin. And negative 273.15 degrees Celsius. Add 273.15, and there you're at 0 Kelvin. So it's the same as the Celsius scale, just offset by 273.15. The importance of the Kelvin scale is that absolute zero is 0 Kelvin. So it's called an absolute temperature scale. 0 means something definite and universal. It means 0 possible temperature, the lowest possible temperature there can be. As opposed to Celsius and Fahrenheit, these are arbitrarily defined 0 points. Mr. Celsius defined 0 degrees on his scale as the freezing point of water. He found that to be convenient. Mr. Fahrenheit, he defined 0 degrees as something else on his scale. Later it got refined so that 32 and 212 freezing and boiling point of waters respectively, that those define the scale. But the point is that 0 on those scales are nothing universal. It was just something that somebody defined. 0 on the Kelvin scale means absolute 0. You cannot have a lower temperature. Kelvin scale is most useful for talking about many things that we will, dealing with thermodynamics, dealing with temperature, because of its absoluteness on the scale. When I talk about temperatures of stars, I will give Kelvin. And I know that for most of you, for most people, Kelvin scale is unfamiliar. So if I say 80 degrees Fahrenheit, you know what that is because you've grown up using 80 degrees Fahrenheit. If I say 80 Kelvin, you're not sure maybe immediately what that is unless you've worked with Kelvin scale before. You might have to do some conversions there. So it's not as easy to think about for most of us than the Fahrenheit scale. So, but when I give a temperature of a star, I'll say that, for example, the sun, surface of the sun is 5,800 Kelvin. And immediately you might be thinking, well, I'm not sure what the Kelvin scale is. Well, it's in the thousands of degrees. And if I had said 5,800 Fahrenheit, you really don't have a good sense of, or most of us don't, how hot that is either. Because whether I say 5,800 Kelvin or 5,800 Fahrenheit, you recognize it as a very, very hot temperature. What's going to be most useful is just comparisons of numbers. So I might say that one star, like our sun, is 5,800 Kelvin, and another star is 12,000 Kelvin. What's most important is not that you have a sense of how hot that is, but rather the relative sense. You can say, okay, the star that is 12,000 Kelvin, that's more than twice as hot as the one that's 5,800 Kelvin. And by the way, if you're dealing in thousands of degrees, a quick conversion, this is just to get a round ballpark estimate, as long as you're dealing in the thousands of degrees Kelvin and above, if you hear a Kelvin temperature in thousands of degrees, just double it and you're going to be near, in the vicinity of what the Fahrenheit temperature is. So for example, the sun is 5,800 Kelvin. In Fahrenheit, that's just under 10,000. So if you double the 5,800, scale it back a little, you're in the ballpark of what it is Fahrenheit. So again, the temperature scales with the sun, the core of the sun, not the surface, but the core is 15 million Kelvin, which is 27 million degrees Fahrenheit. The sun's surface, 5,800 Kelvin, which is 10,000 degrees Fahrenheit. Room temperature is about 294 Kelvin, which is about 70 degrees Fahrenheit. So you can't double the 294. Remember I said the doubling trick only works when you're dealing with large numbers, like in the thousands. By the way, you'll notice that on the Kelvin side, the unit is not degree Kelvin, it's just Kelvin. So 15 million Kelvin is 27 million degrees Fahrenheit. Thermal energy is a measure of the total kinetic energy of all the particles in a substance. So let's go back. Temperature is a measure of the average kinetic energy. Thermal energy is the total energy. So it therefore depends on both temperature and density. So if you take the temperature, think of that as a measure of the average thermal energy, and you multiply by the number of particles that you have, that'll give you an idea of the thermal energy. If you think about in the oven, the air in a hot oven is hotter than the boiling water in the pot. So let's just say it's 400 degrees Fahrenheit. It's very, very high temperature. And there you have those molecules moving around very fast. So they have a very high temperature. The water is cooler than that, only 212 degrees Fahrenheit, meaning those molecules aren't moving as fast. It says, but the water in the pot contains more thermal energy because of its much higher density. So you think about this. If you have an oven on to 400 degrees and you stick your hand in the oven, it is uncomfortable and you don't want to keep it in there for too many seconds, but you can keep your hand in there for a few seconds without getting burned. The water is much cooler at 212 degrees Fahrenheit, boiling point, but you stick your finger in just briefly and it'll burn. And that's weird because it's a cooler temperature. But the reason the water burns, even though it's a cooler temperature, is that so the molecules have a lower average kinetic energy, but there are more molecules. The water is more dense than the air. So you have more of those high speed molecules hitting against your skin and imparting their energy to your skin. So you'll get burned more from the water at 212 than the air at 400. Another good example is you think during the summertime, the air might be 100 degrees Fahrenheit, and you can walk around in that 100 degrees air. Some of us might not be comfortable with it, but you can walk around in it and not get burned for a long period of time. However, you touch the pavement, you touch a metal railing, it's the same temperature, but it'll burn you pretty quickly because there's more of those high-speed molecules imparting their energy, hitting against your skin, and it'll burn you. The second specific example of energy useful for understanding astronomy is called gravitational potential energy. As the name implies, it is under the category of potential energy. On Earth, it depends on an object's mass, the strength of gravity, and the distance the object could potentially fall. I gave you an example before of a rock high on a cliff. Well, here's a van high on a cliff, and so it's got a lot of potential energy. Yes, it does have kinetic energy because it got run off the cliff, but even if it hadn't been going fast, if it just rolled down the cliff, it's got potential energy based on its mass, how strong gravity is, and the distance that it can fall. And the more distance it has to fall, the faster it'll go. The more it can move something or maybe do damage when it hits down below. You look at this picture of somebody throwing a ball into the air. The total energy, which is kinetic plus potential, is the same at all points in the ball's flight. So the person throws the ball up into the air, it gets to its highest point, and it's got high gravitational potential energy because it's high up in the air. And it's got less kinetic energy, meaning it's moving more slowly. And now it starts to fall down. And as it falls down, it loses potential energy because it's losing height. And it's gaining kinetic energy. It's getting faster and faster. So down here, it's lower and it's faster. So it has less gravitational potential energy, but more kinetic energy. The idea of conservation of energy is that its total amount of energy, the potential plus the kinetic, remains the same throughout its flight. How this relates to astronomy: in space, an object or gas cloud has more gravitational energy when it's spread out than when it contracts. And so we have here a large gas cloud. It could be several light years in size, and it will gravitationally contract. So you saw the ball falling down or the van falling off the cliff. Each of these is going to go in towards the center. So there is no up or down in space, but rather gravitationally, everything in this cloud, all the molecules get pulled in towards the center. So they fall inward. A contracting cloud converts gravitational potential energy to thermal energy. So by the time this cloud gets much smaller, all of its particles have lost potential energy. It's just like the ball falling down or the van falling down. Here, all the particles have fallen inward, so they have less potential energy. Conservation of energy says that energy had to be converted to some other form, and it actually becomes thermal energy. So it heats up, it gets hotter, and this is actually how stars are born. They start from a very large cold cloud of gas, and eventually they are relatively smaller hot objects. The third specific example of energy useful for our study in astronomy, in particular a study of stars and how stars produce energy, is what's called mass energy. Mass itself is a form of potential energy. And this relates to Albert Einstein's famous equation that he published in 1915. E equals mc squared. That means energy equals mass times the speed of light squared. Now, this should be a very mind-bogglingly weird thought, that mass is a form of potential energy. Because you think of the examples of potential energy that I've given you so far. A ball or a rock on the top of a cliff, just its position on the top of a cliff, that's potential energy. Gasoline in a car, not the gasoline itself, but the configuration of the molecules. Or a spring that has been stretched. Again, not the spring itself, but just the stretchedness of the spring. That is potential energy. And now I'm telling you that matter, the stuff that you are made of, all the stuff around you, that it is a form of potential energy. And that seems weird because it's a very tangible thing. Well, this is what Albert Einstein figured out, that mass is related to energy. It has an amount of energy that is quantifiable, and it's the amount of mass in kilograms multiplied by a very large number, which is the speed of light squared, and it gives an amount of energy. A small amount of mass can release a great deal of energy. This is the basis of nuclear weapons, such as you see a nuclear explosion in the picture. Nuclear power is such a great source of power for our cities because it is a small amount of fuel and it can give a great amount of energy. And inside stars, this is how energy is produced. Matter is converted into energy. Concentrated energy can spontaneously turn into particles. So this is taking in the other direction. Under the right conditions, energy can be turned into matter. And this is what's done inside particle accelerators. They actually create small particles from large amounts of energy. A little bit of math behind this relationship, energy equals mass times the speed of light squared. Now, just because I'm using the phrase or the concept of the speed of light, I don't want you to think that we're talking about anything moving at the speed of light. The thing that we know of as the speed of light, it's a quantity, and it has much more importance in the universe than simply how fast light goes. It is a constant that is part of the fabric of the universe, the programming of the universe that affects many aspects of how the universe works, how electricity and magnetism work. We just happen to call it the speed of light because when it was discovered, it was that aspect of it that was discovered that it happens to be the speed that light goes. But it is a much more important number than simply that. For our purposes in this class, I want you just to know that it's a large number. It's 3 times 10 to the 8th meters per second. Now in this equation, E equals mc squared, we're actually multiplying by the square of the very large number, which means it is an extremely very large number, 9 times 10 to the 16th. You will not in this class be needing to plug that number into an equation. I just want you to understand it's a very, very large number. So the idea here is when we multiply the mass of the fuel, the thing that we're going to turn into energy, by this very, very large number, we're going to get a very, very large amount of energy. And so, for example, our sun, every second, the sun converts 4 million tons of matter into energy. It's so big, so massive, that it loses the mass of about 4 million automobiles every second that goes by, turns it into energy. Now, on the last slide, I said that the wonderful thing about this relationship that Einstein discovered is that a small amount of matter can be turned into a large amount of energy. Well, inside stars like our sun, we're talking about a large amount of energy, 4 million tons every second. It gets turned into a very, very large amount of energy. In fact, every second that goes by, the sun produces roughly 600,000 times the annual human energy production over the entire Earth. Every second that goes by. So this is why solar power is a much sought after thing. The sun is just putting a lot of energy out there into space, and it's just a matter of us developing the technology to grab that energy, such as with solar panels, and make good use of it efficiently. Let's think about a small amount of energy. The mass of 1 penny, if it could be completely converted to energy, could fuel 2,000 cars for an entire year. So you think about what we use now with combustion engines. You fill your gas tank with gasoline. Maybe it's about a 15-gallon tank of gasoline, and that might last you a week or two, maybe 3 of driving, 15 gallons of gasoline. But if we could convert a small mass like a penny into energy, that would give 2,000 cars a year's worth of driving under normal driving conditions. We don't have the technology to do that, or else we would be doing that, but it just shows there is great potential in this idea of mass energy, potential energy. I've mentioned before conservation of energy, very important concept in physics and astronomy. Energy can be neither created nor destroyed. So all the energy that started when the universe began, the total amount of energy, has always been there. It just changes form. It can change form or be exchanged between objects. The total energy content, not only in the universe, but in any isolated system, is always the same. Now, isolated system, that's physics speak for any object or groups of objects where nothing is adding energy or stealing energy from it. So take this pendulum, for example, going back and forth. It is continuously trading off potential energy and kinetic energy. When it's high, it's got high potential energy. But notice when it's at its highest point, it is momentarily stopped. So it's got zero kinetic energy. When it's at the bottom of its swing, it's got its lowest potential energy and its highest kinetic energy. So this is a good example of conservation of energy. In this video, what have we learned? Where do objects get their energy? Conservation of energy says that energy cannot be created or destroyed, but only transformed from one type to another. Energy comes in three basic types: kinetic, which remember is energy of motion; potential, which is stored energy; and radiative energy. And again, when we get to chapter 5, we'll look at more intently at radiative energy. That is the end of chapter 4, part 3. Have a great day.